Welcome back. Our next talk is by Ari Karchmer of BU. We'll talk about new approaches to heuristic PAC-learning versus PRFs.
Yeah, so thank you. So this is new approaches to heuristic PAC-learning versus PRFs, and it's joint work with Marco Carmosino. So this talk will be all about work with one goal in mind, and that's to prove an equivalence between hardness of learning and existence of cryptography. So what would this entail? Well, we should fix a model for learning and a meaning for cryptography. So today will be about PAC-learning, which is a famous model for machine learning due to Valiant, and one-way functions, which arguably characterize the existence of cryptography through many celebrated equivalences and implications shown throughout the years. So what is it that I really want to prove? That's that PAC-learning Boolean circuits is hard if and only if one-way functions exist. And so what happens if you do this? Well, then you could potentially, if you wanted to, rename Pescilin to Pacifica. So why is that? Well, you would have shown that if one-way functions don't exist, then you've got great worst case PAC-learning of circuits. So this world may be a lot less pessimistic. So what about PAC-learning anyway? So we'll keep this somewhat informal, but concept class C is PAC-learnable if there's an algorithm such that for any Boolean concept in the class, any example distribution row over n bits, there's the algorithm, the learner can output a hypothesis H that approximates the concept over the example distribution with high probability. And in this case, what we do is we allow the learner to interact with an oracle. This is a random example oracle that returns, when invoked, it returns a random n-bit example with a label from F. And this algorithm would be considered efficient if it runs in time polynomial n and 1 over epsilon and delta. 1 over epsilon, 1 over delta. So, okay, so far, it's been very hard to get learning algorithms in this setting, besides perhaps some relatively simple concept classes. For example, 3CNF or decision lists. But on the other hand, there are several interesting relaxations of this learning model. Some in particular are membership queries. So in this case, we would replace this example oracle instead with direct access to the function. So the learner could submit some arbitrary query and obtain the label. Alternatively, you could use the distribution specific relaxation where we would get rid of this for all quantifier over distributions and instead consider one fixed row. And then finally, average case over concepts where you get rid of this for all quantifier and consider some distribution over C that picks some function or concept F. So these relaxations have enabled some progress. And so for example, it's been shown in this model or related models that you can learn random monotone DNFs. So this kind of prompts the question, I mean, were these relaxations necessary? And if so, can we at least benefit from the hardness of the gold standard double worst case PAC-learner? And yeah, so recently, Mikito Nanashima defined like a good canonical formulation of the distribution specific and average case concept relaxations as the your PAC-learning, heuristic PAC-learning. And so we'll frequently state results in this model, which is nice because it's robust under some natural variations and generalizes one of the original average case models that's from Bloom, First, Kearns, and Lipton in '93 for average case prediction problems. So what about those equivalences between one-way functions and other primitives that I was talking about? So for example, each of these primitives on the screen are known to be equivalent, and they fall under the class of minicrypt primitives. And but even primitives that are not on the screen, like for example, public key encryption, are even if we can't go from one of these to public, don't know how to go from one of these to public key encryption, public key encryption implies one-way functions, so in that sense, they're required. And so yeah, that's why we're talking about one-way functions as characterizing cryptography. Specifically among these three, how do we get from one-way functions to PRFs? So Hastad, Impagliazzo, Levin, and Luby showed how to construct PRGs from any one-way function. And then GGM, Goldwasser, Goldwasser, and Micali introduced PRFs and showed how to construct them from PRGs. And so these are celebrated equivalences, but maybe somewhat incidentally, as observed by Valiant, this actually gets us halfway towards our goal. So why is that? Well, we can now prove that one-way functions imply hardness of PAC-learning. You would take some one-way function, map it to a PRG, and then a PRF, and then just observe that a PAC-learning algorithm for Boolean circuits would go a long way to distinguish this PRF, and then you could unwind these security reductions and invert the one-way function. So this by now is sometimes referred to as the trivial direction, but of course, what it's really doing is trivializing the direction. Okay, what about the other direction? So here we want to construct a one-way function from the hardness of learning. We will almost always think of this in the contrapositive today. And it's been considered since at least the early 90s, first by Impagliazzo and Levin, and also Bloom-First, Kearns, and Lipton. And in this direction, there is much less to say, unless we at least significantly relax the problem. Particularly, we'll be talking about the PAC-learning setting. So again, here, we will fix rho to be some distribution D and consider F to be drawn from concept distribution mu. So the rest of this talk will be focused about making progress in this direction. Are there any questions so far?
So are you going to what your PAC is?
Yeah, we'll get there, but well, we won't get there fully actually, but it's the regular PAC-learning model, but instead we're not going to have any for all quantifier over example distributions that we want to learn over. We're just going to fix it to be some distribution D that's known to the learner, and we're also going to sample the function from a polynomial time sampleable distribution mu instead of considering all functions at some class. So mu is over the concept class. Kind of generally, I think all you need to know for today.
So when you say hardness of learning in that model, the quantifier is there exists a distribution D for which it's hard? Yes.
So it would be for the specific D. Yeah. So if it's hard in your PAC model, then yeah, there would exist a distribution D.
Right. So if there exists a distribution D for which heuristic PAC is hard, then you're going to get one-way functions. So,
yeah.
And question about natural candidates or examples of the natural classes which you don't know PAC algorithms if you don't know the candidate one.
A natural class for which we don't have a PAC algorithm
So
in the standard model.
Construct the one-way function.
Well, so I think even at the lowest, one of the lowest things you can think of is our polynomial size decision trees. So I think even in this class, they're conjectured.
So basically, an ideal goal of your work would be this line of work would be to take hardness of PAC-learning decision trees and base cryptography from this assumption.
Yeah. So in that particular case, you can PAC-learning decision trees in classic polynomial time. So it's not, so expensive security, but yeah. So let's do an example. This is a good example, and it always comes with an interesting fact that it's due to Naor and Yogev on a work that was mostly about finding adversarial examples to Bloom filters. But so what they did is define a one-way function based on some heuristic PAC-learning problem. And so how does that one-way function look? It takes some bits r and a bunch of other inputs x1 through xm, and it outputs x1 through xm, and then the evaluations of mu of r. So that's the concept named by r under the machine that samples mu, and evaluated on the input x1. And so these are all then concatenated. So there are two observations to make here. First is that when you're trying to invert this one-way function, the challenge that you get is distributed, the output here is distributed identically to some MY's direct product of samples taken from the random example oracle. And then second, when you invert this, what happens? If you can invert it, you have access to some oracle that does so, then that means you get some coins r prime, which are not necessarily the same as r, but that must agree with the function that is named by r prime must agree with the function that is named by r on at least those endpoints. And so what that means is that you can apply techniques that are from learning theory, often named by the name of Occam's razor or other names like that. And then you can show that if you take as your hypothesis this this function mu of r prime, then it approximates mu of r well. So here are some more or other contemporary results. All of these share a kind of general paradigm in common, where they try to encode a learning problem into a cryptographic or complexity primitive and use the constructive contrapositive proof to obtain a learning algorithm. So first on the screen here is this influential work of CIKK, where what they took was a natural property or maybe even MCSPNP, and showed that out of this you can obtain a PAC-learning algorithm. So this is worst case, but over the uniform distribution and using membership queries. So this is under a couple of relaxations. And importantly, this actually worked unconditionally for low circuit classes like AC0 with mod P gates. And then second, we have Oliveira and Santhanam, who assumed an adversary to non-uniformly generated PRFs, which is a bit of a stronger assumption than we're working with, because we're going to just assume adversaries to uniform PRFs. And they obtained a non-uniform PAC-learning algorithm that uses membership queries for polynomial size circuits. So then Nanashima in 2021, this is the same work that introduced the EuroPAC model. He showed how to take adversaries for infinitely often cryptographic primitives, like one-way functions, PRGs, and PRFs, and obtain a distribution-specific EuroPAC learning algorithm for polynomial size circuits. And then finally, this is even more recently from Hirahara and Nanashima, who assumed a bit of a stronger assumption, basically that we live in Heuristica, and gave this gold standard PAC learner for polynomial size circuits.
On the previous slide. So, sorry, I guess I'm not sure what the takeaway from that slide. I mean, in terms of what results you're going for.
So I'll next slide after the one I just gave has some of our results, but this is an example of how to build a one-way function out of a hard learning problem. Because what I showed you was that based on one learning problem in this model, where we fixed the distribution to uniform here and drawn the concept from mu, you can then define a one-way function that if you can invert it, if you have access to an oracle that inverts it for you, then I can give you a learning algorithm.
And so how this differs from what you want to do is you want to be able to do this from any distance.
Oh yeah. So that's the main, that's the big goal. To be honest, we're not.
No, but I'm
Anywhere
just
close to
trying to
it.
understand where this fits into the broader goal.
Yeah. So in our work, we're giving some improvements on a lot of the results we've talked about so far in a few directions. The first one is to consider a different model of computation, in this case, parallel circuits. So we're going to be working with NC circuits. So for this, we're going to take an adversary for a PRF that's computable in NC and give you your PAC-learning algorithm for NC over the uniform distribution. And then second, we're going to try to achieve better uniformity. And what I mean by that is that instead of working with just one specific distribution over examples, we're at least going to be able to handle random example distributions. So you can think of this as like using some distribution over circuits that sample distributions. And so in that model, we'll take the same PRF adversary for either NC or P over poly, and give you, in this case, a weak double your PAC-learning algorithm for NC or P/poly. And then finally, we're going to achieve better occurrence of security. So on the screen, I've put up robustly often PRFs. So robust sets are a notion of due to Fortnow and Santhanam. Actually, we'll do something a little bit stronger, but not quite almost everywhere. But even this was a direction that was highlighted by Mikito Nanashima in his work as a way to go forward to get the true kind of characterization of Hesseland. Are there any questions about those? Yeah, and so still one thing that's still open is to improve this robustly often PRF to almost everywhere. And really for today, I'm going to keep talking about just this first result. One reason that I really like this result is just the fact that, under the reasonable conjecture that P is not equal to NC, then you could have potentially really strong average case learning algorithms for NC in a way that coexists with one-way functions or minicrypt. Not necessarily particularly likely, but I think it's nice. So a few quick words for context. Our results are going to go for NC to go around this kind of bottleneck of linear depth that's arising from the GGM construction. So to do that, we're going to pull in a construction of parallel PRFs from Nauer and Ringgold in '99. And this is a great construction that uses as a base object something called a pseudorandom synthesizer. And at least so far, this kind of seems like one of the only tools to do this, because it's a major open problem to build an NC PRF from a one-way function or even PRG in NC. So getting this equivalence between these three primitives inside NC. Yeah. Well, you mean inside NC?
I'm saying that if you have an exponentially strong one-way function instead of the usual one-way function, I guess that the NC PRF question will still be hard, but then the PRG in NC might be easy depending on what.
Yeah. Yes, that's right. So I don't know exactly the statement depending on the hardness of the one-way function, but I know that it's under some cases it's possible to build a PRG from a one-way function in NC. But I think the bigger question is PRG to PRF in NC. So I think our results hint at an even better goal, which is to basically try to merge what was going on in CIKK 16 with what's going on in Nanashima's work in 2021. So what would that look like? Specifically, what I'm talking about is trying to live inside the your PAC-learning setting, even in the distribution specific your PAC-learning setting, but inside as low circuit classes as AC0 with mod P gates. Right, so as it stood, there was a huge gap here because this was only for polynomial size circuits, while this was scaling down tremendously. So to explain even more convincingly why we would care about merging these things, we should introduce the notion of weak PRFs. So I think this will also remain informal, but all I really need to say is that weak PRF is basically a PRF that only needs to be secure when the adversary views random points on the function. And so in this case, because of this relaxation, we'll often want to look for really low circuit complexity, even in classes that are known not to admit full-blown PRFs. So yeah, why merge? Well, the special motivation would be to destroy weak PRFs in this class. There are recent works that propose heuristic constructions of AC0 mod P weak PRFs. So in particular, one due to Boyle, Couteau, Guilbeault, Eshai, Cole, and Scholl. And so they're giving heuristic constructions, which just means that there's no reduction to some super standard crypto assumption. And you can still prove things about this, which is, for example, that the candidates are low bias, so they resist linear attacks, or have high rational degree, so resist some kinds of algebraic attacks. But I think, you know, at the minimum, this is, in my view, highly suggestive of the fact that the natural property that was used as kind of a PRF distinguisher in the CIKK work is, you know, as I understand it, not ruled out by these classes of attacks. And so even if you can't get the full goal of getting rid of AC0 mod P weak PRFs, there are interesting subclasses like sparse F2 polynomials, or even AC0 on top of one layer of mod 2 gates. But you know, actually, as it turns out, even this work has candidates in both these classes. So it's no secret that cryptographers are generally winning. But you know, I think at some point they have to lose. Yeah.
So in pure fact, what is the distribution over the concept class that you assume?
Sorry, say it.
So in pure fact, there's a distribution over the concept class as well, right? So what is it that you generally assume? Is it uniform from the concept class? Or?
So yeah, you could just think of it as
Okay.
Like, just to jump in on that, like one of the really nice things about PurePack is that you can translate to any approximately p-sampleable distribution over concepts in the class. Like that's part of why it's a nice canonical model. That's in like the appendix of Nanashima's paper on this. It's a really nice property of the model that stating it for uniform suffices for many of these results.
So the CIKK learning algorithm rules out very strong pseudorandom functions in AC0P. But what I think you're saying is because it uses membership queries, it doesn't rule out strong, weak pseudorandom functions. Strong in the quantitative sense.
Yeah, that's exactly right. So both, you know, so both in the case of full-blown random functions, you still could have
so the question could like address whether the membership queries are really needed.
Yeah.
So if there are weak pseudorandom functions in AC0P, on the other hand, you get a hardness of learning.
Yeah. So the weak pseudorandom functions correspond very naturally to average case learning algorithms.
And hardness is like 2 to the square root n, at least for sparse polynomials. That's a projection. Okay, close to that. Yeah.
Okay, any more questions? I mean, so I think just to finish what I'm saying is that the cryptographers are winning, but you know, I'm not asking you to break LW here. So here's a statement of the result that I'm now going to try to shed some light on. But I'm going to generally describe this result with application of breaking AC0P PRFs in mind. But the techniques are kind of interesting because In some ways, the traversal around DGM seems to enable the other kind of orthogonal looking directions that we're improving on. So I'm not ashamed to say it. If there is one thing I want you to learn today, it's what's a pseudorandom synthesizer. So actually, a quick intermission. I wanted to ask a very quick show of hands. Who here has heard of a pseudorandom synthesizer? Most of the cryptographers, hands up. A lot of the complexity theorists know. Complexity theorists should take home what's a pseudorandom synthesizer. So some basic facts about that. I've put up this kind of spectrum here. One-way functions on one end and PRFs on the other end. Somewhat in the middle, but kind of towards one-way functions are PRGs. And this is giving some undefined notion of complexity that I kind of made up, but PRGs in the middle, a bit closer to one-way functions, and weak PRFs and PRS, very tightly related, also in the middle, but surprisingly, in my view, closer to PRFs. So a little bit of justification for that. In some cases, we can get one-way functions to PRGs with logarithmic blow-up in depth. And from GGM, we can get PRGs to PRFs in linear depth. And from this work from Noah and Ringgold, we can get PRFs from PRS or weak PRFs in logarithmic depth. So what that just means is that if we have some PRS or weak PRF in depth D, then we can get a PRF in roughly depth D log n. But one of the big open questions is, and this would go a ways to improving this relationship a lot, but how to build a PRS efficiently from a PRG. Okay, so pseudorandom synthesizers. Actually, it's pretty much just a PRG, but it's special. It's a PRG that it outputs almost squared as many bits as its seed, and it stretches it in a very correlated way. So I'm going to identify any function for simplicity that so that if it takes 2 n-bit inputs and outputs 1 n-bit output, it will be called a synthesizer. You can define a family of synthesizers, but for today, we can just think of this as a fixed function. And so how do you define pseudorandomness? You use the so-called combination function. So we can take a look at this figure. The combination function takes as input lists of n-bit inputs left and right, and it takes the output of the synthesizer and on every combination from this list. So first, you could take this yellow vector and combine it with the blue vector and get this, place the output in the green square here at index 1, 1 of this matrix. And then similarly, take the yellow and combine it with red. And this is supposed to be orange box here in the top right. And so you kind of get the picture. This fills in this matrix of outputs of synthesizers on combinations. So we say that the synthesizer is pseudorandom if when it's given random left and right inputs, lists of inputs, then the output, this matrix, is computationally indistinguishable from random. Is that clear? So Noah and Ringgold in 1999 gave a construction of PRFs from PRS in log depth. So if you have a PRS in depth D, then you can get a PRF in log depth, D log n. And this is a beautiful construction that induces a very interesting subclass of parallel circuits. So what do those circuits look like? They take at the bottom here, all these circles are key material, and each of these circles is 2 n bits. And so the first thing it does is it takes the input, which is a binary string. In this case, it's an example of 00100. And it will use those bits to select one of 2 circles. So here, the first input is 0, so it selects the left A1. And then the second 0 selects the left A2 and so on and so forth. And then that provides the inputs to a first level of synthesizers. And then you kind of just iteratively apply these synthesizers in a recursive way all the way to the top. So why does it look like in this shape? The synthesizers, we've just defined them so that they always output half as many bits as they took as input. So in log depth, you get to the top, which is just one synthesizer outputting n bits. And I wrote, this is kind of pictured in the case of synthesizer families, where at each level you could take a random synthesizer from the family. But again, for today, we could just think of this as the same synthesizer every time. So by now, I think this should give you a pretty clear map of what we want to do. And that's to use this play to lose method to take a PRS to a PRF. And so first we will encode your PAC-learning problem as a synthesizer, and then use the NR99 proof to access this circuit and turn a distinguisher for that PRF into a distinguisher for the synthesizer, which in turn gives a distinguisher or even predictor for the learning problem. And then from there, there are several standard techniques we can use involving constructing averaging and boosting or hardness amplification to get the full type of learning algorithm that we want. Any questions about that map?
So what is this? You're trying to show that if you've got a hard learning problem, then there's a pseudorandom function in NC.
If I've got a hard learning problem in NC,
Right.
then I've got a pseudorandom function in NC, in particular with log depth. So if the hard learning problem is in NC1, you can compare it to NC2.
Okay, so why do you need the other steps? He's saying, like, once you encode the learning problem as a synthesizer, can you show that breaking the synthesizer would be breaking the learning? Would be breaking?
Yeah. So what I'm now going to proceed to show you is kind of how to get a bit of a more intricate distinguisher to prediction lemma that takes a distinguisher for a synthesizer.
Oh, this is because what it would do immediately is give you kind of a weak learner.
Yeah.
Okay, and now you're trying to like convert this to a strong learner.
Yeah, so actually the conversion to the strong learners, we're not going to get to today, but really for the basic case, this first result I was talking about, uniform specific distribution, those techniques are pretty standard.
Mm-hmm.
I'm going to show you really just one technical obstacle that we have to get through in encoding.
So I mean, so you can't just plug it in, once we have a synthesizer, then we get a pseudorandom function, because you're actually going to be doing this iteratively during the boosting. And you're going to need to like apply it recursively.
It depends on the boosting. I think in the uniform specific case, you could just use hardness amplification because it's contained in NC. It's not that big of a problem. But in the cases where you're handling random example distributions where these types of techniques don't work because they're inherently specific to the distribution, it's a little bit more complicated. And for that case, we say in weak learning. I mean, it's what one could, imagine ways to try to boost that, but yeah. So what's one technical obstacle here? And so I think what that is that the PRS just has so much correlation. It's not like a typical PRG. And that means that the kind of classic distinguisher to prediction lemma is not like Yau's. And it turns out that it's a real legitimate computational problem to sample hybrids for this PRS. But if I may, what ends up happening is that you have to find a way to merge reality, which is information that comes from the example oracle that you have access to, with a lot of counterfactual information that's sampled kind of inside the learner's head. So how do you encode a synthesizer? Again, mu is a distribution over concepts. Let's say it requires m random bits. Rho is a distribution over examples requiring r random bits. And we'll assume that we have some evaluation machine that takes as input a concept f and an input x and outputs f of x. So the synthesizer will sample r random concepts and m random inputs, and then print all combinations of these. So this is using a combination operator similar to the one that was defined for the pseudorandomness, but actually this is just inside the synthesizer. So why did we do that? That's to keep the kind of invocation of the NR99 code as simple as possible, and obtain something that takes two inputs of the same size and outputs one output of the same size. I'll just draw up one more comment. If you were here for Mikito Nanashima's talk yesterday, he was talking about dualization of learning problems. And so I think one thing you may notice here is that this type of synthesizer, in a way, seems tightly connected to that, in the sense that you're kind of dualizing for free here. Because, and what I mean by that is that you're taking many representations of concepts and many representations of inputs and combining those, but in such a way where if you think of maybe just the columns versus the rows of the output of the combinations, they look like the duals of those problems. So in a picture, this is what it looks like. But as I said, when we think about pseudorandomness of the synthesizer, what we're actually looking at is combinations of synthesizers. So we've got this block matrix interpretation here, where each row is labeled by coins to sample concepts, and each column is labeled by sets of coins to sample inputs. So there should be some colors here that aren't showing up. So if you want to direct your attention to the screens or just listen carefully for these indices. But this gives a natural way of defining sequences of hybrids. First thing you might do is pick a block matrix within this outer matrix here. In this case, I've picked H22. And to the right of that, so to speak, you'll fill it in with random bits. To the left of that, it's honest evaluations of the synthesizer. And then inside, you'll do something similar. So this is kind of a folded multi-dimensional hybrid thing, where again, you'll pick an index and fill it to the right with random bits and to the left with honest evaluations of the synthesizer. So this is great. But one trouble is that you have not figured out how to incorporate actual information from that's provided to you from the example oracle. So what does that entail? Well, first of all, by picking this hybrid in the example, we've kind of implicitly decided that this is going to be the so-called guess bit that's scrutinized by the distinguisher. So that means that at the minimum, you have to fill in the challenge example. In this case, it's written as Z in that column. Okay. And also, by virtue of this being the guess bit, that means that example or labels in this row need to come from F star, which I've written to mean the real concept that's housed inside the example oracle. So that's great inside H2 too, but this introduces other correlations. So for example, if you take a look at the green highlighted squares, first start with U21. This is in the same row as H, which means that it needs to share the same concepts. So in particular, the third row of U21 needs to also have information saved from or taken from the example oracle. Why is that? Because the third row here in H22 is real labels from the example oracle. On the other hand, U12 is in the same column as H22. So that means that it needs to share the same examples. And even though we don't know the coins that were used to sample Z, for example, that's okay, because we've kind of bypassed this distribution by sampling it blindly from the example oracle. So we fill in the same example portions as kind of halfway past the coins and halfway into the computation of the synthesizer. And then, this introduces more correlations that are kind of third order at this point. So the red blocks or pink blocks, U11, same row as U12. So that means you need to use the same concepts, but also it's the same column as U21. So actually, all the coins have been determined for U11 already. So as you're sampling everything else, you need to carefully keep track of all those actually images of coins and reuse them here. Hopefully that gives you a quick idea of that. I think it's important now to see, so what does the actual hypothesis look like that you output here? This is a picture of that. So it kind of hooks in an input at the top here that goes in a Z, and you use a bunch of random bits to sample a bunch of counterfactual concepts and data to sample this particular row of H22. And then you're going to go through that process of sampling this data structure correctly, which is combinations of the synthesizer. And then you're going to hook that up to a distinguisher for the hypothesized distinguisher for the PRF and NC. So every time that wants to make a query, you kind of send that to the code written into the reduction of NR99 and use this data structure to answer it and kind of proceed interactively until the distinguisher is satisfied. And then, one can argue that whatever the distinguisher outputs is in some sense evidence for the prediction, and you can get a weak learner out of this at least. Any questions? So it's also useful to kind of look at the difference between this and CIKK, because again, the goal is to see how far we could scale down. I think the first thing to observe is that synthesizers are a bit like Nissan-Wigderson designs. So CIKK used Nissan-Wigderson as the PRG as a kind of viewed it as a PRF. So why are they kind of similar? Well, in both cases, you're applying a fixed function to subsets of the seed. In the way that I just showed you, they all have pairwise intersection n. And so the NW designs have much better stretch. So there's many more of these sets, and also they have smaller intersection. But using the synthesizer, we were able to get rid of the membership queries. But the drawback, I guess, is that the NW PRG is just so directed that it fits inside AC0 mod P. While the code that we need to use from the reduction of NR99 introduces depth, logarithmic depth. So I'll just finish with some open problems. I think the first thing is getting really anything for the class of circuits that's induced by running the NR transformation on, for example, sparse polynomials. And what we end up showing is that any non-trivial distinguisher for this class of circuits implies a non-trivial Heuristic learner for sparse polynomials. So again, that may be difficult, but there are plenty of subclasses that you could look at. For example, AC0 composed with one layer of mod 2 gates. There are weak random functions conjectured here, so again, may be pretty difficult. But I would say that even new proofs of old results would be very interesting. And the reason for that is that, so as an example, the work of CIKK, it seems to not be able to scale down further to AC0. And that's because the designs cannot be computed in AC0. And so it doesn't seem immediately able to reprove some known learning results. Whereas, in this setting, we're not suffering from that. There's no immediate barrier that prevents scaling down further. So even if it's something that we know doesn't contain weak random functions, it may be interesting to get a learning algorithm this way. And so I think the bottom line is just that, these are frontier learning classes, and it's not totally clear to me that these have been attacked with concrete distinguishers to predictors. And then maybe a couple more open questions that are just cryptographic in nature. So I don't think it's really been considered much if PRSs can live inside NC0. We don't suffer from the same problem as weak PRFs, which cannot be in NC0 unconditionally, because they're kind of a hybrid between PRGs and weak PRFs. And in particular, such PRSs and NC0 would I think now imply optimal constructions in terms of depth of PRFs. And then finally, along the same vein, constructing PRSs from PRGs in a more direct parallel construction. And I think I'll stop there.
Questions?
Go back a slide, sorry. How should I interpret this in our bracket XOR?
Yeah, so this notation is supposed to mean transforming synthesizer that's computed XOR those demands as part polynomials into that kind of tree-like structure.
Okay, thank you, sir.
What's like the smallest circuit class you could reasonably hope for this kind of composition? Like if I have C, so there's a tree-like thing, yeah, like maybe it could be smaller. Does it have to be long depth?
I mean, no, I don't think it has to be. So you could think of trying to do some kind of circuit depth reductions. Again, like when you put yourself up against sparse polynomials or generally AC0 with mod P gates, at that point you'd have to refute some conjectures. So those cryptographic conjectures imply a possibility of certain kind of circuit depth, but if you restrict enough, I think, like I said, at some point.
Break until 11.